Um, Welcome and thank you for staying to this last lecture. That will be something completely different from everything you heard today. There won't be a single line of code. uh, my name is Matej Peranić, and unlike most of you here today, I'm not a cybersecurity expert. I'm an experimental physicist. So I will talk a bit about quantum physics and how can we use quantum physics in the terms of security and communications. To start with, I don't want to bother you too much with physics and quantum, but I feel like I have to introduce some basics so that I will refer to later on. So when we say quantum physics, what are we actually talking about? So we are talking about effects that we see the nature behaves on the scales or on 10 to the minus 10th, which is basically when we get to the level of atoms and smaller. In this lecture, I will mostly focus and talk about photons, basically particles of light. And when we get to these scales, we see that the nature behaves a bit differently than on our everyday scale. One interesting thing is that we see that the matter exhibits properties of both particles and waves, which you learned in high school probably that light has these properties. And as a consequence, we cannot describe the nature like we can describe it in macroscopic scales, but we have to use probability and statistics. This leads us to the principle of superposition, which basically says that, well, if you have a classical system that can have, for example, if you measure it and it can have two outcomes. For example, I have this coin and it can have head or tail. In quantum systems, they have this superposition principle that says while you're not making a measurement, they're simultaneously in both of these states, which we can imagine that it's going on when I flip this coin, and while the coin is in the air, we cannot say that it is in one or the other state. We can say that there is 50% of chance that we'll measure it, the state of head, and 50% that it will be tail. The important thing here is that I make measurement to get the information of the state of the system. So what we say is that the measurement actually disturbs the state of the quantum system, which is an important property that I will refer to later. And this superposition principle basically enables us to introduce quantum bits or qubits. So unlike the classical computing where we have 0 or 1, in quantum computing and qubits can be represented with probabilities and statistics. The other property is entanglement. Quantum entanglement says that if you produce two particles, let's say two photons, in a certain way, in certain conditions, they will behave as one system no matter how far they are. So if you make measurement on one particle, it will be the second one that is entangled with this one will be immediately affected. So if anything of this sounds strange, that's okay because it is strange for us on our macroscopic level, and it was strange even for Einstein, who said entanglement he called spooky action at distance, and for the superposition there is this famous quote that he said, the God does not play dice. So he was very skeptical about this interpretation of quantum physics, but it's basically the best we have, and all the experiments are confirming it. The last thing I will say about this quantum and physics theory is the so-called no-cloning theorem, which basically says that it is impossible to clone quantum state. And based upon these properties, we can look into quantum technologies that have been developed recently. There are three main areas I will mention. First, we have quantum computing, which I will separate into quantum development of quantum computers and quantum algorithms. So when I say quantum computers, development of quantum computers is mostly building a hardware, and quantum algorithms are basically then the code that you can run on those quantum computers to use to make it useful. Then we have quantum communications, which I will mostly talk about today, and some ideal goal of quantum communications would be development of quantum internet. What is envisioned as the quantum internet? Well, basically interconnected quantum networks. So what are quantum networks? Quantum networks are basically full mesh networks, so networks in which each user is connected to any other user in the network, but their security and their communication is based it's quantum safe, no matter is it post-quantum cryptography or quantum key distribution. I will mention that later also. And the third big field is quantum sensing and metrology. So using these properties, you can make use of quantum systems to develop more accurate and more sensitive devices. So first of all, quantum computers, threat or treat. So we are building them because we have the idea that we can make something useful out of it. So due to superposition principle that I said, they have the ability to explore multiple solutions simultaneously and decide which is the best solution for a certain problem. There are different realizations. For example, superconductors. Those superconductors are in general materials that when they don't show electrical resistance, but the problem with superconductors is that these materials show this property only on low temperatures. When I say low temperatures, I mean really, really low temperatures, below 1 Kelvin. So then the other branch of development is the so-called topological qubits. You have maybe recently heard of Microsoft's Majorana 1 chip that is based on these topological qubits. Then photonic qubits, where you can basically encode your information, like I already mentioned, in photons, in some state of photon. For example, you can use polarization of photon to encode information. So how can you do that? Well, basically, I guess you maybe remember from the high school what is polarization. So the waves can travel like this. So then you can call that vertical polarization, or like this, and then that's horizontal polarization. And then you can say, okay, if I measure that the incoming photon has vertical polarization, I can call that 1, and if it's horizontal, that's 0. And basically, then by measuring number of incoming photons, you can get a string of these bits or qubits. When talking about qubits, I will just warn you, when you read some news about quantum computers, they often says, oh, we've developed new chip with I don't know how many qubits. Be careful what they're saying and what they're talking about, because there is difference between physical and logical qubits. Physical qubits are actually the true quantum systems that are on the chip itself, that can be, I don't know, quantum dots, whatever, atoms, whatever. And logical qubits is basically those qubits that are useful. So, like I already mentioned, for example, for the superconductors, even the slightest, for example, if they absorb some energy, they will be disturbed, and those qubits won't be functional anymore because they won't be in the state that you can control. So there is a difference between physical and logical qubits. And there are several ways of dealing with that, one of which is, okay, you can say, let's build a chip with as many as physical qubits possible, and we will encode the same information in a lot of them, so if some of them are not working, okay, we have a backup. But that's problematic because then you have to control everything, and then you have a big hardware. And the other approach is to try to reduce the difference between physical and logical qubits. That's the direction called error correction. So basically, you try to reduce the noise in the system so that the number of logical qubits is as closer as possible to the physical qubits. So we are building them because we believe they can help us to solve some problems that classical computers are not able, or it would take a lot of computational power or a lot of time for these problems to solve. Some of which are optimization problems, simulations of some quantum systems, search problems, and so on. What I'm trying to say here is basically you can imagine building a new material or building a new drug. Instead of creating new material with slight changes and then doing some experimental testing on them, you can basically, we believe that it will be possible with quantum computers to make simulations of that, and then you will reduce the cost of creating a new, large number of new materials and testing them. However, there is this possible problem, is that quantum computers are good at solving. We believe they will be good at solving the problems on which classical security relies upon. So the most famous one is factorization of large numbers and Shor's algorithm. You probably heard about that. So we can think in the direction of, will they replace classical computers? They probably won't replace classical computers. Like I said, they're good at different things. How far are we from functional quantum computer? Well, we already have some functional quantum computers, but also the question is, what do you mean by functional? In the context of security, we can ask ourselves when will quantum computers be good enough to be a real threat for our classical security protocols. And the estimation says about 10 to 15 years. Like maybe 5 years ago, the estimation was 10 to 15 years. So we basically don't know. That's the problem. So are they actually a real threat? Well, I would say they are, because the real threat, so what we know about development of quantum computers is basically what we are giving. So the companies that are producing quantum computers are giving us some information about the development. And mostly we have, I don't know, IBM, we have Google, we have Microsoft, we have some private companies in US, in Australia, working on that. And they all have, this Western world actually has nice divided. So we have government, then we have military, we have scientific community, we have some companies. And there is some money going from the government to scientific community to the military. Scientific community usually gets its funding through some grants. And when you get some grant, you have to justify the money that you got. So you have to publish some papers. You have to say, oh, I did this, this, and this. So basically, we know what's going on the West. But what we don't know is what's going on the East. So when I say East, I mean basically first of all, China, for example, because all this, like I said, government, military, scientific community, everything is blurred out. And we don't have the trace of money, and we don't know basically what's going on, because if they don't have to justify the money they get for the development, we don't know what they are working on. And I will just here give a parallel to this AI hype that we are currently at. So you've seen what happened with the DeepSeek. Nobody knew basically what they were developing, and what they did is they took hardware and knowledge from the West. They developed something much more efficient and for much less money than the West. And the problem is that we don't know what's going on in this area. I will mention some things that we know, but the threat, I would say it's real, and we can maybe monitor what's going on the West, but not so from the East. So basically, we can wake up one morning and they will announce that they have functional quantum computer possible to break classical cryptography, and then we are in a problem. So what are the possible solutions? Well, there are two big streams. One is post-quantum cryptography, and the other one is quantum key distribution. Here are some properties of these two approaches. Post-quantum cryptography, the easiest way to explain it is basically it's an extension of classical cryptography methods that we have. So they're based on some mathematical problems that are believed to be hard to solve even for quantum computers. The good thing is it does not require additional hardware. It's scalable and compatible with existing protocols. The question is it good enough? So if we are developing something that should protect us from a threat that has not yet been fully developed, how do we know, is it safe? Is it good enough? On the other hand, we have quantum key distribution. So post-quantum, the main difference is that post-quantum cryptography can be implemented on this more software level. Quantum key distribution is based on the fundamental laws of nature, and it's more focused on the protection of the infrastructure. However, it does require additional hardware. There is an authentication problem, so the authentication is not solved inside of the QKD protocols. And there is a distance limit because due to attenuation, you have to, in classical communications, you can use repeaters. Like I said, here you cannot use repeaters since repeaters would make measurement. If you make measurement, you will disturb the state of the system. It can work on the existing telecom infrastructure, so basically I mean fibers, and it is absolutely secure. When I say theoretically, to the level of implementation, so ignoring the problems, possible problems with the equipment or noise or something like that. So the protocol itself, it's safe. So these are some pros and cons of each of them. But as you can see, where the PQC is bad, QKD is good, and vice versa. So the question PQC or QKD, I don't think that's the right question, because I believe that in the future we'll use it simultaneously, both post-quantum and QKD. So I believe that many of you are already familiar more or less with post-quantum and the classical protocols. For sure, you know them better than I do, so I won't go into details of PQC. I worked mainly with QKD, so I will just explain what is the main parts of QKD and this absolute security, where does it come from? So I will jump straight to one of the protocols with an entanglement-based protocol, and we'll read this from the top to the bottom. So imagine that you have two parties that wants to communicate, Alice and Bob. and they want to build secret key. So how can they do that using QKD? So here we have source of the entangled photons, and those entangled photons are being then sent towards Alice and Bob in some way, fibers, free space, whatever. Alice and Bob, they have some devices that can measure incoming photons depending on their polarization. So they have some polarization analysis modules, and they can make measurement in two bases. We call this horizontal vertical base, and this is diagonal anti-diagonal base. Those are basically polarizers, and polarizers are basically our sunglasses. So polarizers are basically transmitting the light of certain polarization. If you have horizontal polarizer and you have incoming horizontal photon, it will transmit. If it gets vertical, it won't get transmitted. What they do, they basically make measurements. So they count photons they receive, and they keep the results of the measurements secret. So Bob has his string of results of his measurements. Alice has a string of results of her measurements. But what they do then, they publicly announce which basis did they choose to make these measurements. If someone is listening to this public channel, they don't get the information about the results, and they're one step behind Alice and Bob. They cannot do anything with the information of basic choices because Alice and Bob are actually comparing them, and where they use the same basis, they decide to keep this bit, as you can see here. In that way, they create secret key. Shared here means in a sense that's shared among them, not publicly shared. So why is this absolutely secure? Well, so like I said, if someone tries to break listen public channel, they're one step behind. But what if someone tries to eavesdrop here in the infrastructure, so someone wants to tap the fiber or something like that? So if they try to make measurement, like I said, by making a measurement, they will disturb the state. And Alice and Bob, in their security analysis, they will notice that. What else can they do? An eavesdropper can try to make measurement and make a copy of that. But, like I said, there is no cloning theorem that says, oh, you cannot copy a state of a photon. So basically, an eavesdropper cannot interrupt, they can interrupt this distribution of photons, but they will be noticed. How? Well, Alice and Bob, they're measuring these photons, and they're in parallel measuring something called quantum bit error rate. So it's basically they measure how many photons they receive is in the wrong polarization. Let's put it in that way, the easiest way to explain. And for the entangled-based QKD protocols, this quantum bit error rate should be below 11%. If it's higher, then they can discard the key and start the process all over again. So there is possibility that somewhere there is some noise, there is always some noise, there is some disturbances, they will influence and on the quantum bit error rate. All of that, just to be sure, is pointed to an eavesdropper. So now when we've shown how to connect two users, we can ask, okay, how can we create a full mesh network, a network where each user is connected to every other user? So one idea is to entangle more photons. So if you have 10 people, you can entangle 10 photons and distribute them towards each of them, but that's hard to produce and hard to maintain. So the approach that is usually taken is to create photons. So this source, sorry. So this source of polarization, so this source of entangled polarization photons it's producing photons of not only one wavelength, but the distribution of the wavelengths looks something like this. And then we can choose pairs of photons of different wavelengths and distribute them among all users in the network. They're centered around 1550 nanometers, which is standard wavelength for the in-fiber telecom communications, because there is minimum attenuation on that wavelength, and this distribution of photons basically corresponds to standard ITU channels. So the logical table looks something like this, and this is the example of a quantum network that we built at the University of Bristol with 4 users. Each user is basically receiving 3 photons of 3 different wavelengths that are connecting each user to every other user. This is the example from the network with 6 users. We've just show you the secret key rate that we measured. This is basically the result that we got. Here we had some T1, T3, T2, and T3 stands for the time when the detectors had their cooling cycles and so on and so on. We had, even during night, we had some breakage of electricity, unexpected, but you see that everything is more or less stable. Depending on the noise in fibers, they had more better or worse results, but we were happy with this. So what are the existing implementations? I already mentioned China. They have the longest QKD backbone in the world, from Beijing to Shanghai, with different topologies in different cities. And also, upon not only that, they have a dedicated satellite called Misuse to QKD. So with this satellite, they have demonstrated the first video conference call protected by QKD with Austria. Why with Austria? So the person who is leading the development of quantum technologies in China, his name is Pan, and he is a student of Anton Zeilinger, who was the main person in Austria for the development of quantum technologies, and Zeilinger won a Nobel Prize in physics for the development in this field a couple of years ago. So basically they have a person who is directly worked under the Nobel Prize winner, and they have unlimited, basically, resources for in this field. This is the example from UK. I was in Bristol working on their implementation of QKD network. In Reading, there is a big telecommunication hub, so it's almost halfway between Bristol and London. In Cambridge, Cambridge is a good position because R&D facilities of Toshiba are in Cambridge, and they're working mostly with them. And I think that in Ipswich, they have a ground station where they do experiments in free space with satellites. Where is Europe? Well, Europe realized a couple of years ago that it's that we are miles behind, especially behind China and United States. So they have decided to invest some money in the development of quantum communication infrastructure. And there is ongoing project called EuroQCI. They have decided to give some money to every country in Europe and to develop some infrastructure. As you have already seen on the example of the UK, some countries already have some infrastructure. For example, we didn't have, so this is a good project for Croatia to develop something. So there is an ongoing project also in Croatia. I think that it lasts till mid-2026 or something like that. The last big thing they published, they said that they did within this project is they have deployed dark fibers between institutions that are working on this project dedicated to QKD. So they will use it for further tests. And here, this project is, the institutions in these projects are some scientific institutions like Ruđer Bošković Institute, Institute of Physics. Then there are Odašiljači i veze, Karnet, Srce, and some institutions like FAIR and some other faculties. The funny fact is that, interesting to say is that basically the first QKD implementation between different countries was done between Croatia, Italy, and Slovenia. And I've put this picture here so that you can see that basically some of this equipment is already plug and play. You can find more details in this paper about how they used it and how it was conducted. The outlook for this field, well, USA is mostly focused on the post-quantum protocols. Their National Institute for Standards and Technology, they had called for papers for standardization of PQC protocols, and there were 4 rounds of submissions, and they have selected some of the protocols for different things in the for the PQC, while other countries are also investing in QKD, which is also potential for companies if you are working in the development of, for example, in telecom company, or if you're working on a new hardware or so, but also what can you do in your companies to get quantum safe? Well, you can identify critical assets, make an inventory of sensitive data and systems, and develop a timeline and strategy for transition toward PQC or QKD, whatever is more relevant for your company. There will be probably some transition period when you'll have some hybrid approach with classical algorithms and PQC upon QKD, and to regularly update risk assessments and strategies. Something that you probably all know about, but I think that you should also consider it in the terms of quantum threats. So, should we implement quantum safe solutions? Well, I think you know what is the answer. So, I don't think that's really the good question to ask. Maybe a better question would be, when should we implement quantum safe solutions? And although this topic is maybe look into the future, I would say yesterday. Because, like I said, if I were you and if I were a cybersecurity expert, I would always think in the worst case scenario. The worst case scenario is that, okay, someone already has fully functional quantum computer that can break classical algorithms. What would be the consequence of that? There will be some data leakage, and someone would already have some comparative advantage in some field of economy or, I don't know, military or whatever, and we would notice that. What is the second worst case scenario? Okay, no one has today fully functional quantum computer, but maybe they will develop it tomorrow, in week, month, or so. What will they do with it? They will gather, again, some informations and so on, and for some period of time, we basically won't know that they have it. So we are in the same situation as the worst case scenario, so we won't know at first that they'll have it. That's why it's important to be proactive and to secure yourself from the possible threat. Like I already mentioned, I think that this development will go in the potential of hybrid PQC and QKD implementation, where PQC can be layered on top of QKD. PQC can protect this software level and be developed on the software level, while QKD will protect critical infrastructure. At first, I'm sure it will be in governmental institutions, for military purposes, and so on. And then combining them, basically, you can get a single key for further encryption and communication. And that would be it. Thank you for your attention. And if you have some questions, feel free to ask.
I got a question. Thank you for a nice lecture. Really interesting. I got a bone to pick with this whole quantum area, to be honest. And I liked what you said, that in the end you need a hybrid solution. So what puzzles me is a lot of people are, so companies, not companies, nations, European Union is investing a lot of money to actually finance the networks to do quantum key exchange and distribution. And okay, you demonstrated China does this over long distances, but that's only to negotiate for a key, basically. But when you do get that key, in the end, to send large volumes of encrypted data, you're going to still be using the normal high-volume backbone of the internet for the massive transfer of data. Just the encryption key exchange will be done through QKD.
Yes.
And the way these algorithms, and now correct me if I'm wrong, for key exchange work is that you get basically a binary key, which doesn't have any properties except being basically very random and secure, which means it's good for symmetric cryptography.
Yes.
But not for asymmetric. And we still need asymmetric encryption for a lot of things. Yep. So for our world to exist as we know it, we still need digital signatures, asymmetric public key encryption, which still has a problem of key exchange, which we don't solve basically with QKD.
Yeah, you're right. So QKD is only for symmetrical key exchange, and it cannot be used for asymmetrical. So there is no, as much as I know, adoption of QKD for that. Yes, correct.
We are missing that.
Yeah, we are missing that, but I think that there is you have to start from somewhere.
Oh, that's true. Yeah.
So you can build upon this if you get that's the whole thing. So you have classical now encryption and algorithms. You will get something a bit better with PQC, but you don't know how often maybe you'll have to refine it due to fast development of the threats, possible threats. And then you have a part of your communication that you can protect also with QKD. Mm. Yeah. So it's not a full solution.
Yeah.
Yeah.
Good.
Correct.
Thanks.
Thanks for the question. Anyone else? Okay.
If I understood correctly from the presentation, in order for the quantum cryptography to be implemented properly and in a secure way, you need specialized equipment.
For the QKD, yes. So like I show on the protocol, you need to have, for example, if you want to implement this entanglement-based protocol, you need a source of entangled photons, which is something that you normally don't have, and you need to have detectors. Those are critical, critical points. When I was looking into NIST recommendations, they recommend to go towards PQC, and they said they have 5 reasons why QKD is not good enough. 3 of those are basically considering how to say it, technological development of QKD. So they say, oh, you need dedicated infrastructure for that. When I started working, for the analysis of incoming photons, each user needed 4 detectors. Then when we worked in Bristol, we managed to do this protocol, this analysis with only 2 detectors. I've read now that they've developed a protocol that uses only 1 detector. So I think that this is more a question of technology, and it will go on, and it will be better and better. And I don't think that technology, the development of technology should be stopping us from getting into somewhere.
The reason why I'm asking is because I've seen post-quantum implementations that exist, and I am aware that some software, for instance, Signal, already implements, or at least states that they implement quantum algorithms to be post-quantum safe. But then my question is if this is just words, or is this actually properly implemented and you can count on it that it's post-quantum safe?
Okay, so post-quantum, as I mentioned, what I said about the additional hardware is considering QKD. And post-quantum cryptography is something that you can apply on the existing infrastructure. So I don't know in details, I cannot tell you, is it proper implementation or not for this certain scenario, but the advantage of post-quantum cryptography is that it's basically just you take classical protocols and you extend them to be safe from what you believe that will be threat from quantum computers. And you don't need dedicated additional hardware for it.
Thank you for the question. I saw one hand here. Okay.
Hi.
Hi.
Thanks for the presentation. I have a question regarding the implementation of a network that will support quantum key distribution.
Yep.
What is more feasible, or what will be less expensive to do? Like to use fabrics and connect the whole world with fabrics, or maybe go with the satellites?
Okay. I mentioned in one slide that the bad thing about QKD is the problem of high losses and the distance limit, so that you cannot use repeaters. So for the approach will be probably combined. So if you want to use it on the metropolitan scale, you will use in fiber. And then if you want to connect the whole world, for example, you will have to use satellites. And therefore, you will need also some hybrid points where this key exchange will go between metropolitan area towards satellite to connect it with other base ground station.
Okay, thanks.
Anyone else? No?
It's the last lecture. He's keeping you here.
I feel something going my way. One thing that's also probably maybe a big stepping stone for, I would say, worldwide adoption is the cost of this technology. So, you know, everybody today uses basically some kind of cryptography every single second. So my phone just updated 5 times while I spoke to you. And everything is encrypted, and there is some key exchange going on. But it's unlikely that this phone or my PC at home or even my large desktop will have, in the next 10 years, the hardware to do proper key exchange. So it's more likely that it will be like a service. And if I'm depending on, let's say, a service, and there's like a cardnet or something that has the facilities to do QKD, and then sends me that key through a normal network, again, then it's probably no longer safe for me. So as you said, it's probably going to be just for military or high grade government, something like that, but they can have facilities. And for me, if I want to do proper key exchange, I'm going to probably have to write something on a piece of paper and give it to someone that's going to be more safe than anything else.
Similar thing with quantum computers. You won't use quantum computers to do PowerPoint presentation. Or you won't have quantum computers that sits next to your desk.
Yeah.
You will probably you will connect to it through cloud or something like that. Also with QKD, since we'll probably wait for some time to get the hardware on the level that it won't be as expensive as it is today. But the first government, military, and then banks, hospitals, big data centers, they are probably the first users of QKD. For example, in Switzerland, they're already implemented QKD in some banks, and they have a lot of referendums and voting. So this infrastructure is already they have implemented for that infrastructure QKD.
Yeah. Maybe just a comment. Probably, this whole audience knows. Maybe that's new for you. Maybe it's not. There's a really big craze now in the security community about post-quantum cryptography. Everybody's like, that's like it's almost like AI. It's almost as AI. And everybody's talking that you have to have it, as you said yesterday. Everybody's saying all the algorithms are dead, even though basically all in RSA is semi-dead with short algorithm. Not even elliptic curves are dead. All the symmetric stuff is perfectly fine, and everything which is actually encrypted is encrypted with session symmetric keys, and only the initial exchange of those keys is encrypted with something like RSA, for instance. And nowadays, all pen testers, everybody tests that are TLS handshakes have perfect forward secrecy, so you cannot save it and decrypt it later. So I haven't seen a single analysis of how much actually the key exchanges nowadays over the internet is actually really vulnerable to future quantum computers, because how many of them don't have forward secrecy and really do use only RSA algorithm. I haven't seen an analysis, but they're screaming that everything is dead. So I think it's a hype.
It's a bit hype, but and it's not that because everything is still working. But the problem is that the situation here, there is no gray zone. Basically, it's white or it's white or black. It's 0 or 1. Once you'll have it, you'll be in problems. So you don't know when will it happen and when will it happen. So I think that's a problem. That's why this whole hype is. And when you look into these analyses, they all say, okay, there is also this harvest now, decrypt later type of attacks. So let's get everything ready for that.
Thanks.
No problem.
Hello. Could you perhaps explain what's the actual fan out of this system? Because to me, it looks like a point-to-point connection, pretty much, because the internet doesn't work that way. The first time you hit a router or something, you have to re-encode data from what I'm seeing here. Yeah. And compared to OpenBSD's N-chain, that version of the lattice encryption seems to be more likely to be implemented compared to something like this, as I'm seeing it right now.
This is all. So what I showed, this is point-to-point. And I would have to check, for example, the real-life implementations, what they did, what they did after this point-to-point exchange, and what did they do with a key. The results and the schemes that I've shown you were basically results from the scientific research. We worked on the problem of how to deal with disturbances in the communication channels. So we weren't so focused on the life cycle of the key and what happens with the key afterwards, but more into solving some more technical issues here.
Are we done? Yeah. Thank you, Matej, for this